probably make an assumption of an irrotational flow, certainly not near the solid wall. And this is the basis of the boundary layer theory. So the boundary layer theory doesn't describe the vorticity flow, but it divides the flow region into two parts. One a small layer, depending the smallness of the layer will depend on the Reynolds number and so on, which will be discussed shortly in the next topic, right? But it assumes that the flow is irrotational outside the boundary layer, and you can see that that is not it's an approximation, but it is an approximation motivated by the physical consideration of the vorticity being generated near the solid wall. So you cannot neglect it in the entire flow region. Are there any questions? This example illustrates the idea. If you go back and probably look at other one-dimensional flow problems that we have considered and see the effect of using the vorticity equation. So we don't have time to go into detail, but this should certainly serve as an illustration of the idea. Now the second problem is very simple. We have done the flow of a fluid through a past sphere. What this problem again from BS is that all he's saying is that replace the boundary condition. So the solution is the same. We have to replace the boundary condition. One of the boundary conditions, we assume that this is the linearly viscous fluid, so we assume that both Br and B theta vanish on top of the solid sphere. Right? So that's a no-slip boundary. But here is saying that it is a Newtonian fluid around a spherical gas bubble. So it is a gas liquid interface rather than a solid liquid interface. So what he is saying is that the interfacial shear stress will vanish, and this he says implies the vanishing of the theta component of the velocity on the surface of the sphere. And finally you have the equation. So you have to convince yourself that what he is saying is consistent with the final equation. So in terms of solving the problem, all you have to do is to replace. I'm talking about the second problem now in the assignment. So the second problem you have to go back to the problem we consider the flow through a sphere. Right? So flow past a sphere, and this is a linearly viscous fluid, two-dimensional flow. Same idea, but there is no spherical gas bubble, he says. So he says everything else to a good approximation will remain the same. So only equation is the same. Vr at r theta, I think it was, is 0. That remains the same. So what is in B theta of r theta? That's on the surface of the sphere. He says equal to 0, we assume there. So he said this will no longer hold because it's not a solid sphere but a gas bubble. Right? So this has to be replaced by the following condition. Somewhat complicated condition to apply probably. I haven't tried it myself. At R, what he's seeing is the vanishing of the theta component is to be replaced. So here the theta component is not vanishing. He says this is because the interfacing shear stress can be assumed to vanish. There is continuity of stress across the gas liquid interface, but you have to convince yourself that that means that this is actually equal to 0 for the function f. Right? I'm not going to go into that. But you can simply, for the case of solving the problem and getting the velocity profile that are given here, you can simply go through the mechanics of solving the problem using this boundary condition instead of this and see if you get the answers that are given here. Right? Treat that as an exercise, it's an extension of the problem of the flow past the sphere. Everything else remains the same, only one boundary condition is different, and that leads to a difference in the velocity profile, and also the probably, I don't know what happens to the force, is probably remaining the same. Expression for the force is also given. So you have to go through the whole applying the correct boundary condition, calculating the constants, right? And then the infinity boundary condition remains as it is. And I haven't written here the r going to infinity. That you have to retain as it is. The b infinity comes in the expression. Everything remains the same except one of the boundary conditions. The eta at the surface vanishing is being replaced by this new boundary condition. You have to get the new velocity profiles and calculate the expressions for the force and verify. Now we go to the third problem. Find the streamlines and particle paths for we have calculated streamline and the particle path. First, let's take a look at the streamline. Right? So, Devan Kumar, when you come to the board and solve this problem, where is Devan Kumar? Can you come to the board? Yeah, okay. First come to the board, that should not be a problem. Streamline, I will write down the equation. The streamline is what I want to find is x1 of tau, x2 of tau, x3 of tau. Streamline is given by the xi by the tau is the I equal to 1, 2, 3. So now we solve the equation, that's all it is. So you should know what are the equations to solve. Right? So the time has to be kept fixed. You can fix it as a d star or d bar. That is not going to come into the integration for the streamline. So integrate this dx1, right? dx1 by d tau, and integrate that. Let's see. dx1 by d tau equal to d1. Can you write that? What do you get? Yeah, d1 is equal to x1 by 1 plus t, fine. Now integrate this with respect to tau. Good. Log x1. You can choose a particular initial, not initial actually, particular condition, parametric condition. So I put xi of some tau naught, let's make it 0 for convenience, is equal to xi naught. So we can integrate from tau equal to 0 to whatever value of tau we want. Yes. Yeah, and you have x1 naught also. You have to put that. That's not taken to be 1. Log of 1, that's fine. You can write it here. Naught. Right? So that's fine. Tau times 1 plus t. So what would be, it's very easy to write down what is the equation for x2. This is only the x1, x2 plane, right? V1, V2, so V3, x3 we don't have to worry about, right? So the streamlines will be in the x1, x2 plane, so I don't have to consider the third dimension at all. The third component of the velocity is 0. So write the corresponding expression for x2. Yes. 2t times tau. Yeah, fine. Yeah, fine, good. Here, can you come and finish the problem? I'm calling you. So, what do you need to get the streamline? You cannot leave it like this. This is a streamline, right? But I want it as a curve in the x1, x2 plane with the parameter being removed. If I want to plot it, for instance, I can plot it like this. So can you get it? Can you combine the two and just have x1, x2 tau has been eliminated. How will you do it? Nothing else needs to be eliminated. E and so on will come into play. So we have, so write it here clearly. So that you can see, yes, you mentioned it. So write the final expression. This also as yeah, that's fine. This is carried out. You cannot, yeah, this is not quite correct. This seems to be correct. Right? So I could probably take t over to one side and then write this as I can write it like this, and then I can. This is somewhat confusing to write. This is multiplying the logarithm, not within the logarithm. Right? So I can maybe write this as x2 by x2 naught raised to the power 1 plus 2t by 1 plus t is equal to x1 by x1 naught. That's one way of writing. Right? So I just this is multiplying the logarithm. So I can take the logarithm of x2 by x1 raised to the power. So I want to remove the logarithm from the picture. Right? x2 by x2 naught raised to the power 1 plus 2t by 1 plus t is the logarithm of that is equal to the logarithm of, which is what I have. Then I remove the logarithm, and this is what I have. So you should clearly see that this depends on time. So the streamlines are going to vary for different times. Right? That's very important. So time, so I fix one time at a certain time, let's say t prime, and I'm going to get one curve, one set of streamlines. Right? Then I go to another. So what are the set of streamlines? This is a particular. So at a particular t prime, right? This is the streamline, but we have a set of streamlines. So what distinguishes one set of one streamline in that set from another streamline? The time is fixed. So how are we going to get infinite number of streamlines effectively? By changing x1 naught and x2 naught. So if I fix the time, this represents a whole bunch of streamlines. So what distinguishes one streamline from another in that bunch is our choice of x1 naught and x2 naught. So if I fix that, I will get the streamline passing through x1 naught, x2 naught. Right? So that's very easy to plot here. So you can plot this and see how it is going to look like. Right? So I choose the point x1 naught, x2 naught. So if I, and of course t prime is fixed. So if you understand clearly what is meant by this equation, it's easy to integrate and get these expressions. You understand the significance of this. So I fix a t prime. So this is now fixed for all the streamlines I will be generating. These are all the streamlines at a particular time t prime. Right? So I fix t prime. So t is equal to t prime. So now by choosing different values of x1 naught, x2, if I choose one value, so then I get a streamline passing through that. So I vary that. Right? So I can choose x1 naught prime, x2 naught prime, x1 naught double prime, x2 naught double prime. Then I get another streamline passing through that. So I generate as many streamlines as I want at this time. Then I can go to another time and do the same thing. Right? So then I generate all possible streamlines at all times. Yes.
But x1 not x2 not the streamline would start at that point because we are integrating from 0 to tau.
That's fine, but tau can also have negative values. It's only a parameter. Right? It can also have negative values. It can go back also. Integrate backwards also. You choose the tau appropriately. Right? But you can integrate back and then generate the streamline over the entire space. Tau is for convenience, we are choosing it to be a parameter to correspond. So what we are effectively saying is the value of the parameter tau equal because there is an infinite number of parameterization possible for every curve. You have one parameter, you can think of the infinite number of parameters. So the choice of tau is entirely arbitrary. So what we are saying is that we are choosing, suppose I fix x1 naught, x2 naught, then I am saying that corresponds, assume that corresponds to tau equal to z. Right? Tau is finally going to disappear from the picture. I can choose another value of tau, call it some tau naught, right? But it is not going to affect the way the streamlines are going to look finally. So the best way is take a very simple thing to plot and see how it is going to look like. So this is the anyway, this is the final expression for the particle, streamline. So now, to understand, as I said, the earlier case, we saw that one of the examples I probably picked from Aris is also maybe is from the same book. But the point here is that in that particular case, even though it was unsteady flow, this is also unsteady flow. There, the streamlines and the particle paths were turned out to be the same, surprisingly. That can also happen. Here, we have to see what happens to the particle path. So the particle path has to be looked at slightly differently. So that is dxi by dt. dt now comes into play. This is the particle path. We are directly dealing with the velocity. There, we are looking at the velocity as a tangent to the streamline. That's why the equations, even though they look very similar, right? They have quite different meaning. Now what about the particle path? The particle path will be pi. And then here, xi at t equal to 0, I call it psi I. I equal to again 1, 2. And here the integration is with respect to time. Right? So, now how would you do it? Jacob John, and you do integration. Well, you have to, once you know the formula, you can manually apply it and get the result. But you have to also understand what they mean. So can you integrate this now? So I have to write it out for you. dx1 by dt is x1 by 1 plus t. dx2 by dt is x2 by 1 plus t. So now you integrate this and substitute the initial condition and let's see how the particle paths look like. Here the time will come into the integration. Here it was just looking like a fixed quantity. Yeah, put the initial condition properly. Don't, I hate putting these integrals which have no limits at all. Lead to all kinds of confusion. Maybe you like that uncertainty, but I would like to be certain about what I am writing on the board. Yeah, it is not x1 naught, but it is actually psi 1. So I wanted you to shift that because this is like tracing the path of a particular particle. Right? So we are following, this is like following the material coordinate, what happens to it. So that's why I am deliberately using the same notation that I used for the material coordinates earlier. So I am fixing a particular fluid point and I want to follow its path with respect to time, and also obviously we are following the path of that particle, so we have to describe it in space as well. But finally, I plotted it on the x1, x2 plane here because x3 component is 0. Removing the time from the picture, then we get the particle path projected onto the x1, x2 plane. The time is a variable here. We're projecting it onto the x1, x2. You can see how the curve, that's why we can compare streamline and particle path. Because finally we are looking at curves in space. That you should understand. It's pretty much plotted, right? So, yeah, right. Finally complete x1 by psi1. So the logarithm can be very easily handled here. Because on both sides we are having the logarithm. The factor 2 will have to be taken in doubles, cannot just be removed as a constant. So that will give a square root effectively, right? So the 1 plus 2t, yes. This is not quite what I want because I want to remove t from the picture. I want to plot it. Right? I wonder how would you eliminate t? Can you think about it? Because that's also one final step. This integration is very how would you remove t from the picture? You can solve for t very easily from one of the equations and substitute it into the other. This is easy to do it here. Right? You have to do it anyway, you can leave it. This is the correct procedure. So what I would do is simply this clearly means x1 by psi1 is equal to simply 1 plus t. So I can write t as x1 by psi1 minus 1 and substitute it into this. Right? So the final answer can be very easily obtained. Right? So we want to reach that final state. So the second equation is x2 by psi2 is square root of 1 plus 2t. So I can write this as 1 plus 2t equal to x2 by psi2 squared. So which means that, or I can leave it like this also. So I get x2 by psi2 is equal to 1 plus 2 times x1 by psi1 minus 1. Put a square root here, that doesn't matter. This finally is, now you can very clearly see, is describing a curve in space. Right? Time is there, it's suppressed, because finally when I want to see a curve in space, the parameter is merely a 2 here, the curve, to get that curve, to make it very concrete, because you're looking at the tangent vector, so the curve comes in. Finally, when I say it's a curve in space, here is a curve on the plane x1, x2. I want to see an equation between x1 and x2 alone, nothing else should be there. However, psi1, psi2 will be there because that is what I fixed. Now what I do is, I will now plot, right? So now what are the particle paths, right? So I have to now choose the psi1, psi2. So I will choose psi1 prime, psi2 prime, and I generate a curve. I choose psi1 double prime, psi2 double prime, and then I get the particle path corresponding to that material point, right? That is what it is. Time is suppressed in this, right? But if you want to see the effect of time, you have to go back to the equation. That is at what time a particular point on this curve corresponds to. That can be easily formed. So that is very important to understand. This distinction, so clearly you can see that from the form of this, what would you say? Are the streamlines and the particle paths the same? They are not quite the same. Right? They are different. That you expect in general, especially when you have an unsteady flow. Right? So that is what is expected. In the earlier case we saw, when we saw the earlier was somewhat untypical, where the streamlines and the particle paths coincided even though it was unsteady flow. Not necessary. But in general, that is a typical case that the two will not be the same. For steady flow, you should be able to prove theoretically the two will effectively be the same. Right? So that's what. So if you plot one of them, you will get the other. Are there any questions on this? Yes. Yeah. So that is the origin, right? Here it is the way it is written. It's not maybe there are no. In this case, when you put t equal to 0, x is equal to 1. That is it's not written in a way that I can answer, but you can probably look at it this here, sin 1 by. So if you get t equal to 0, sin 1 equal to x1, so that is the coordinate. Yeah. Probably this form, but you can easily get what you're asking is that if I choose sin 1 to be 0, right, then you get x1, that is the position at t equal to 0. What you're seeing, I understand. How could you get the particle path passing through if the point is at the origin, not the reference time, may not be, might become problematic here, but we may have to be able to rearrange the equations and get that. Is equal to x1. That's what these equations that's what we have imposed. So it's not surprising we are getting that. Right? But this question is, I think you're asking. If I put sin 1 and sin 2 to be 0 here, then you have to equal dividing by 0. But then at that point where sin 1 and sin 2 are 0, x1, x2 are also 0. We cannot really directly appeal to that equation. Actually, you are having a case of a 0 by 0.
That is the case that we are having velocities also 0 at point velocity. That is, a particle is not
moving at all.
Will be all progressive.
Yeah, the velocity is also 0. So it remains there. That's what you're saying. That point remains there. Yeah, so maybe it's not a very physically meaningful input. It's given just to help you generate the streamlines and particle paths, right? So you should not probably look very deeply into the physical meaning of this, or whether this is what this means, that such a flow is possible, right? But certainly it helps you to go through the motion, because typically what you have is you have to do the numerical integration. What you have is the velocity data is given at discrete points, and you have to somehow put it into your integration routine and generate the streamlines or the particle paths. But this is to just show the procedure of how to generate it analytically. For that we have to consider some simple analytical expressions, and that's what we get. Okay, so to answer what you are saying is that if the velocity is 0, then the particle remains there. So that is the particle path for the origin. So you cannot really look into this equation and try to see what would happen, because at that point x1 and x2 also see, right? So is that okay? Is that the I think that's reasonable. Any other questions? we still have a few minutes here to try to complete this problem. I'll just go through quickly the procedure and outline what you're supposed to do. The fourth problem is irrotational flow past the sphere. We have done the cylinder, and so you're asked to here you're given the potential itself is given. This is now the spherical polar coordinates. Actually, what is asked for is quite easy. Once this is given, right? Because B is all you have to go is to. It involves only differentiation, so all you have to go is to go to the formula for the gradient in spherical polar and simply carry out the differentiation and you will get ER and B theta. That's easy to get, right? But also you should try to solve the additional problem of getting this itself. Then we have actually got it for the cylindrical flow past the cylinder. How would you get the phi? It has been given to you, so it's easy to do the rest of the problem. How would you calculate the phi itself? What equation would it satisfy? Laplacian of phi is 0, so it's the same. So you have to set up this problem, the same sphere. I don't know how, actually probably not the full details are given. Maybe you can go to problem number 4b5 and see how the coordinate system is and what is the direction of the velocity far away from the sphere, what he has chosen, which direction the fluid is going. Probably it's going in the z direction, if I'm not mistaken. But anyway, the important thing to recognize is that this is the same for all irrotational flows. Particular geometry, the particular dimension, here is a two-dimensional case. That will determine what the final expression is. The boundary conditions will be very similar to what we had. So this is the exact analog of the cylinder problem which we have solved. So it will be worthwhile for you to actually solve this Laplacian equation because the answer is given. Impose the boundary condition would be 1 at r to infinity, right? And then the condition on the surface of the sphere, again you will find that the no-sphere boundary condition clearly is not satisfied. If you look at the expressions that are given, again B theta is not 0 on the surface of the sphere. So what you should do is simply apply the r component of the velocity vanishes on the surface of the sphere, and then you should be able to solve the problem and get the expression for the theta component. The exact equivalent of what we solved for the cylinder. I would like you to go through that, right? The coordinate system and so on. If I have it, I will write it down. But you can go and easily check that in the problem of the first to it. Yeah, I think what he has is actually sphere is here. This is the z-axis, and he's considering flow in the positive. So B is actually B at r going to infinity is actually V infinity times Ez. That is the direction of the flow. That you have to keep in mind. The cylinder we have slightly different. The coordinate system is different. So solving that, right? And then you have the boundary condition. This is the boundary condition for r going to infinity. So you have to convert it to boundary conditions on Br and B theta, and then convert it to boundary conditions on phi, same as we did for the cylinder. And then the other condition is Br at r equal to r, theta is equal to 0. With these two boundary conditions, you should be able to actually derive this potential for it. That's a more difficult part. I would like you to go through that and see how the solution looks like. Right? So you should do that. And then the rest of the problem is very straightforward. You can get the velocity by using this. The pressure profile, again you have to choose suitably. Maybe a point is chosen right through the z-axis. This might be the infinity point. And then you have a point on the surface. You can apply the Bernoulli equation. Only for a perfect fluid we can get the pressure profile that is given. So you have to assume that it's probably stated in the problem. Right? It's only for a perfect fluid. So it's the same problem that we have solved for the cylinder. We have to go through it for the sphere and get all the potential as well as the profile. So the final problem is again irrotational flow. The immediate function that comes to mind is the potential function. Right? So now going back to the cylinder, this was the problem. I'll just outline the purpose behind giving this problem. You know, we get a fifth problem. It is again irrotational flow past the cylinder. But now you are asked to solve it using the stream function rather than the potential function. Now, because here we are considering V to be only ERC plus E phi, only two components we are assuming to be present. And further, ERC is a function of RC phi, and E phi is also a function of. So this conditions clearly satisfy for this case. Even if the flow is not rotational, we would obviously use only the stream function, right? But however, here we have further given the condition of irrotational flow that can also be solved using the stream function. Now, the stream function definitions are given to you. There's a pattern in the way the stream function is defined, because in the continuity equation has to be satisfied. You will get derivatives of BRC with respect to RC and d phi with respect to phi. So the BRC is related actually to d psi by d phi, d phi to d psi by drc, but the sign and the other factors that come in have to be accommodated to satisfy the continuity equation, right? So you can very easily verify that this would satisfy the continuity equation. That's what the first question is. And then you have to prove that the Laplacian of psi is equal to 0. This is known for irrotational flows. The additional condition you get. The additional condition that you get. So you have to show that when you impose the condition of irrotational flow, the stream function actually satisfies the same equation as the potential function. So are the two going to be the same? Yes or no? They both satisfy the same differential equation. Can you conclude that both will be the same for the irrotational flow past the cylinder or not? Yes or no? Quick answer. No. Why? Why they will not be the same? Huh?
But capital P does not satisfy the continuity.
That's true, but that's not the. Yeah, the two are different functions, so you expect them to be different, right? But in terms of, they satisfy the same equation. So what will make them different? They, constant what? What is different? When you are given an equation, and then you have to update the solution. What additional information you need? The boundary conditions will obviously be different for psi. Because the definition of psi in terms of velocity is different. We now give you an exercise. So actually the boundary conditions are, in terms of the velocity, are the same as we assumed earlier for the potential, but you have to now translate it to conditions on psi rather than phi. So this gives another angle to help you familiarize with the solution of the problem. Solution, the form of the function would be the same. You can immediately write it whatever we had, RC power lambda and all that. Right? That will be the same because they both satisfy. But the coefficients will certainly be different because the boundary condition that psi satisfies would be different from what phi stands for, right? Because this is for sine, and if you want to express it in terms of, right, this would be minus d phi by d rc, completely different actually. And then d phi would be minus 1 over rc, d of the potential with this. Obviously, you expect it to be different, right? And so we have to now use this. The boundary condition, the velocity is the same, far away from the cylinder, whatever we have assumed earlier, you can assume the same thing, v infinity times Ex or whatever. Then on the surface of the cylinder, right, you should assume only this condition, VRC. And clearly you should get an expression not only for the answer is not given for psi, but a good test is that whether it gives the same velocity perfect. So the point here is that you have to start with this equation, apply the boundary condition, get psi, and then obtain the velocity profiles. Those would have to match with whatever we got from solving the Laplacian of phi equal to c. Right? So it's an indirect check on your whether you've got the psi right or not, is when you finally calculate the velocity profile, whether they are matching with what we have got for the cylinder using the potential function. This sort of completes the cycle. So whatever we have not done for the case of the sphere, we are doing it for the cylinder. Right? What sort of completes all possible problems you can look at in the irrotational flow past the cylinder or the sphere. Right? Are there any questions? Yeah, phi is formed from this with the boundary conditions, right? The same as we had before, limit rc going to infinity. V is V infinity Ex, I think that's what we had. And plus this, these two boundary conditions, but now we have to convert those two boundary conditions on sine. You can see what that would be, and then that will determine psi. It will clearly be different from, we can look at the answer in tomorrow's class, right, and see what is the difference and how psi and phi are actually related. There's an important relation also between psi and phi in terms of, which can be expressed in terms of theory of functions of a complex variable. Right? We'll take a look at it if we have time tomorrow. And then we'll move on to the next topic, which will be on brief discussion on boundary layer theory.